Yes, so let me start with reminding some notation. T and H bar are greater than 0. And F, U star are from the torus cross the set of probability measure on the torus into R of class C2. Let me say C3. And so again, to say that this is of class C3, you look at this function as a function defined on the Hilbert space. So if you quotient the Hilbert space by a relation, you get the set of probability measure. And the C3 mean with respect to the differential structure on the Hilbert space. And let me recall that the so-called mean field game equation is to find given mu, a probability measure on the torus, find W from 0 T cross the torus into R. Find sigma from 0 T to the set of probability measure on the torus, such that the derivative of sigma with respect to time plus the divergence of sigma gradient of W equal to negative H bar over 2 Laplacian of W dtu W plus 1/2 gradient W squared plus F of Q sigma T equal to H bar over 2 Laplacian with respect to Q of W, and sigma at time T is mu, and W at 0 Q is U star of Q sigma of 0. And another reminder, important fact to remember. Assume I have a function U from the set of probability measure on the torus into R of class C1. And let T goes to sigma T be a path in the set of probability measure. V be from 0 T cross the torus into RV be a vector field, be such that the partial derivative of sigma with respect to T plus the divergence of sigma v equal to 0 in the sense of distribution on 0 t cross the torus. And the integral from 0 to t dt, the integral on the torus of v of tx squared sigma t dx is finite. So here sigma t means sigma of t. Then if a v is a gradient, or v is approximated by a gradient, if you differentiate u of sigma t, you get the gradient of u at sigma t, vt sigma t. So by this, I mean the integral on the torus of the gradient of u at sigma t of z, vt of z, sigma t dz. So this is true for L1 almost every t. However, if I know, in addition, that v is continuous with respect to time, almost every t will become every t. Okay, so the function t goes to sigma of t is locally Lipschitz. Therefore, it is differentiable almost everywhere. However, if I have some additional continuity property, I will know that it is differentiable everywhere, and this equality will become everywhere. Now, let us compare this to that. Okay. So the gradient mu of u at mu is a map from the torus to R. Now let us compare this to that. Remark. If you compute the Laplacian of sigma, this is the divergence of sigma, the gradient of log of sigma. Because the gradient of log of sigma is the gradient of sigma divided by sigma. And so if I multiply by sigma, I get the divergence of the gradient of sigma. Therefore, in the mean field game, if I call this I, and I call that 2I, hence, in the mean field game equation, 2I is equivalent to dt w plus divergence of sigma gradient w plus minus h bar over 2 gradient of log of sigma. No, plus. First, I need a correction here. This is sigma. This is I. And that is plus. Therefore, if I compare this equation to that equation, my velocity is v equal to gradient q of w plus h bar over 2 gradient of log of sigma is the velocity. And so, if I differentiate a function u at sigma, I am going to obtain this where I replace v by that expression. You are right here. No. Here? Here, yes. Sigma, thank you. So the guess of Leon was this system of equation, I can reduce it into one equation. Such that, so I can find a u which will depend on t, q, and mu, such that you satisfy a certain equation, and the u will allow me to construct sigma and to construct w every time you give me mu. And let us do some heuristic, some formal computation to see if such a u will exist, what equation it will have to satisfy. And that equation is the master equation. Assume there exists a function u from 0 t across the torus, across the set of probability measures on the torus in R, such that if dt sigma plus divergence of sigma gradient q of u of t q sigma t equal to 0, equal to not 0, negative h bar Laplacian q of u. Okay, so let me pause here to say that give me an arbitrary u. I ask myself, can I construct a sigma such that this equation is satisfied? Start covering this. Assume that h is 0. A sufficient condition to be able to construct such a sigma is it is enough to have that u is Lipschitz with respect to the q variable. Now, the argument becomes a little bit subtle, but you can do it if this term appears. So if you give me a u which satisfies some smoothness condition, anytime you give me a mu, I can find a sigma, which I can find a unique sigma, which is solution to this equation. So assume that there exists a U such that if I define sigma this way and set W of TQ to be U of TQ sigma of T. So it should not be assumed, it should be let U be such that define sigma and set W to be that. What is the equation? Should you satisfy for W to satisfy the mean field game equation 2I. So the first equation, the first mean field game equation is satisfied trivially because if I differentiate W with respect to Q, I have that it is the derivative of U with respect to Q. And so the first equation is satisfied. And the question is, what condition I need on U for the second equation to be satisfied? And once we identify this condition, we are going to call that, this is what Leon called the master equation. So solution, we are going to use that result. Differentiate W with respect to Q. You get the gradient of U at T, Q, sigma of T. The Laplacian with respect to Q of W, T, Q is the Laplacian with respect to Q of U, T, Q, sigma of T. Now, I am going to compute this derivative. The time derivative of W at TQ is the time derivative of U at TQ sigma T. Now I am going to use the chain rule and that property. So this will be the derivative with respect to T of U at TQ sigma T plus the Vassel's time gradient of U at TQ sigma T Vt sigma T, where Vt is a velocity where V is the velocity for sigma. But that velocity is given, according to that, it is given by V T of Z equal to V of Tz equal to gradient Q U of T Q sigma T plus H bar over 2 Laplacian Q gradient Q sigma according to Thank you. Yes. Log of sigma. So now let us compute this. But let's associate gradient u of t q sigma t v. So I am going to denote this vt of z. Vt of z sigma t is the integral on the torus of the gradient mu u of t q sigma t applied to z. Vt of z will be, here it will be z, because there I call it z, and the variable here will be z. Gradient q of u of t z sigma t plus h bar over 2 gradient q of log, and I am going to write it gradient q of sigma divided by sigma t at z, the whole thing sigma t dz. So I am going to split this into two terms. The integral on the torus gradient mu u of t q sigma t z inner product gradient q u of t z sigma t dz plus this thing. But I can simplify that by sigma t and integrate by parts. So I'll have a negative h bar over 2, the integral on the torus, the divergence with respect to z of gradient mu u t q sigma t of z. And I will be left with a sigma t. Minus h bar over 2, the integral over td, gradient, divergence of z, gradient mu of u t q sigma t of z. Sigma t of z dz. Therefore, M, G, F, I, 2I, this equation is satisfied if and only if I replace this derivative by dtu of t q sigma t plus I use the fact that the gradient of W is the gradient of U. And so let me finish with this term. This term is plus the integral over CD, gradient mu U of T Q sigma T. inner product gradient Q U of T Z sigma T sigma T of Z dZ minus H bar over 2 the integral divergence Z of gradient U T Q sigma T sigma T of Z dZ. So I have written this, and then I'm going to write that plus 1/2 gradient Q U of T Q sigma T square plus F of Q sigma T equal to H bar over 2 Laplacian Q of U of T Q sigma T. That is the equation. You must satisfy. In particular, it will have to satisfy, the equation is true for every t. It will be true for t equal to capital T. So when I replace t by capital T, then I replace sigma by mu. But I can vary my capital T. So here capital T is an endpoint. But I am saying that this computation, which I did, even if I apply it at the endpoint, I can apply it anywhere. So I can replace sigma T by an arbitrary mu. So here I can write T mu, T mu, and so on. So I will end up with since mu is arbitrary and sigma T equal to mu, you must satisfy dTu of T Q mu plus, I am not going to copy this, I am going to give a name to it, 1/2 gradient Q of U of T Q mu square plus F of Q mu plus a non-local term, T Q mu equal to H bar over 2 gradient Q of U of T Q mu, and U of 0 Q mu is U star of 0 mu. Here, NH bar of T Q mu is what is there. The integral of the torus gradient mu U of T Q mu applied to Z gradient Q of U T Z mu sigma mu dz minus h bar over 2, the integral on the torus divergence with respect to z of a gradient mu u t q mu mu dz. And this is a non-local operator, which you can write as n h bar. It depends on gradient q of u, and it depends on gradient mu of u. Oh, yes, thank you. So that is called the master equation. So if you can show that this equation has a solution, immediately the mean field game system has a solution. And there are many other things you can produce from the master equation, which is the reason why it has that name. So when you have a problem like this, a difficult problem like this, what you need to know is what is the heart of the matter. So what do you need to understand to be able to solve that equation? And what you need to understand, you can write it in 2 lines. I am going to write an ODE we all can solve. And I'm going to say that if the solution of this simple ODE are smooth, then you can solve the master equation. So let me consider then a special ODE. Given mu PD and S in 0t, solve. And this is just Newton's law. The second derivative of S at t, S q, is negative the gradient with respect to q of f at S t, S q. S t, push forward mu, S at SS is the identity, and the derivative of S with respect to time at 0, S q, is the gradient u star at q, S 0, S push forward mu, and here it is S 0, S q. So if this was not there, and that was not there, this is a familiar second-order differential equation. Now, when you add this thing it means that you can start by solving your differential equation dTs equal to negative gradient Q f of S sigma t, where you assume that the sigma t is given to you. And so this problem is a fixed point problem. If you give me sigma t, I can solve this. But is there a way that if I define sigma t to be this way, and then I solve the equation, I get S back? You integrate this twice. So when you want to solve a second order ODE, you integrate twice. You write that S is the double integral of this, and you see your fixed point problem. And you just need to check that you have defined an operator in the good space and so on. So having existence of solution of this, and this is why we need it, we could solve it only for short time. Having existence of solution of this and uniqueness for short time is not a difficult problem. Yes, so let me say that I have not said that this is related to mean field game. Yes, but this will be related to mean field game only if H is 0. So in the sequel, set H bar to be 0. And if H bar is not 0, then you are going to write the force accordingly. So the force, your sigma, this is sigma t. This is sigma. You are going to write the Laplacian of S push forward mu. You are going to add that in your equation. So observe that if I change the mu, my solution will change. So S, in fact, is a function which depends on T, S, Q, and mu. It is convenient to write it this way. I am going to say that the initial condition is S, my variable is T, mu is the density, and I apply to Q. I am going to use this notation. The solution of that, when it is unique, I am going to denote it that way. So let me state. I will not call it a theorem. If I write all the assumptions, I am going to distract you from the main idea. So let me just state a theorem without assumption. Define U of S, Q, mu, to be U star of sigma S 0 mu push forward mu, and here it will be sigma S 0 mu of Q minus the integral from 0 to T, and I am going to write F of sigma SL. Maybe the simplest way to write it is let me call this sigma of 0, where I set sigma ST mu Q mu push forward mu is a sigma of T. And of course, you see that although I wrote sigma of 0, it depends on the mu and S. And so here, it will be sigma of L dl. And there I need to write the velocity. So V, I have V S T mu of Q square over 2 plus, where sigma T is defined this way, and V S T mu is defined as the derivative with respect to time, sigma S T mu. Composition, sigma S T mu inverse. Okay, so the assumption I postpone is I am going to show that this sigma is invertible. And so what I wrote is correct. In fact, if you consider this capital sigma as Lagrangian coordinate, what I am writing here, if I don't want to impose that sigma T is invertible, I am going to write that dt of sigma T S is there exists a velocity I am going to write that there exists a velocity v such that this relation holds. However, if I knew that sigma is invertible, then my v is defined that way. So theorem, define u this way. If sigma is smooth enough, then u is a solution to the master equation. So this is telling us that the whole difficulty of the work is to study smoothness property of this ODE, this system of differential equations. So what I am going to do, let me start with some rigorous statements. And then during the last 2 hours, we are going to prove that theorem. Theorem. There exists, if T is small enough, and small enough depend on the data F and U star, Then Newton's law has a unique solution. Furthermore, if you look at this application in terms of S, T, S, Q, mu, goes to sigma S, T, mu, Q, is Lipschitz, is of class C1. T, S, Q goes to sigma S, T, mu, Q is W to infinity. Sigma S, T, Q is invertible. And if we set S, St, mu to be the inverse, sigma St, mu, then T, S, Q goes to S, T, mu, Q is W1 infinity. Okay. So what I am going to do, I am going to assume that this theorem is true. And then I will tell you how you show that the theorem is true. So you show that it is true by approximation. You look at the measure mu, which are average of Dirac matrices. And then you check that the Lipschitz constants are bounded by something which is independent of n. And so if you let n go to infinity, this is why you have W2 infinity instead of working in a CK alpha, because the Lipschitz constants are bounded. But if you have W2 infinity, then you get C1, except for this variable where you have to check that you get C1. So let me write some useful property. So proof later. Properties. Let T naught be in 0 T. And set sigma T naught to be sigma St naught mu, push forward mu. Then the following hold. If I go from S to T naught mu. And I compose that with T naught T sigma T naught. I have sigma S T. So I have this semi-group property. And I would like to warn that I have a mu here. I did not put an arbitrary measure here. I put a measure which is on this, the orbit of this path. And so if you replace sigma T naught by an arbitrary measure, there is no hope to show that such identity holds. Now, if you look at classical theory, in classical theory, you have the map doesn't depend on a measure. And so we are back to the semi-group property of differential equation. We also have that if you take the velocity, right, this V is in fact the velocity of the particle. If you take the velocity at S T mu, if you take the velocity at T naught S sigma T naught, you get the same thing as the velocity at S mu. Once you prove this, and you use this definition of V, then the second statement becomes trivial. And so what we need to prove is we need to prove the first statement. So proof. We have to prove that sigma S T mu composition S T naught mu. We have to prove that this is sigma T naught T of sigma T naught. So if I know that my function is invertible, showing this identity is equivalent to when I move this here, I can show that identity. To show this, define S bar of TQ to be this thing, sigma T ST mu. Composition, sigma, composition S T naught mu. And we are going to check what is the differential equation satisfied by S. If it satisfies the same differential equation with this, with the initial and final condition, then by uniqueness, we have proven the claim. So let us start with the easy one. Observe that S bar of T naught Q, so this is Q. This is sigma S T naught mu, composition S T naught mu. And since these two things are inverse of each other, we get the identity. Okay, so that equation is satisfied. We have dt S bar of T equal to dt sigma T, sigma ST mu, composition S T naught mu. Therefore, and so this implies that dt S bar 0 Q equal to dt sigma S 0 mu, composition S T naught mu applied to Q. But this is how sigma, the derivative of sigma at time 0 is defined. So that is equal to the gradient U star of sigma S0 of mu applied to S T naught of mu of Q. And then I have sigma S0 of mu applied to mu. Now compare this to that. You see that it is gradient U star S bar 0 Q. And this second one, I am going to write it as sigma S0 mu, composition S T naught mu, composition, the inverse. So I'm composition sigma S T naught mu. Because these two things are inverse of each other, so that is, let me apply it to mu. However, this, by definition, is a sigma T naught. And that, if I look at there, it is, this is S bar 0. And so it is S bar 0, push forward sigma T naught. Therefore, this condition is satisfied. So the following sentence mean I don't want to do it. It is clear that if you differentiate twice S bar 0 S bar of TQ, you get negative gradient Q F of S bar of TQ, S bar of T, push forward sigma T naught. And the idea of the proof is, you differentiate this twice. And then you use this trick, which I use here. And you get that this is satisfied. By uniqueness, S bar T equal to sigma S T naught, sigma T naught. Use I. I will come back to the proof of I next time. 2I, sorry.